As we mentioned in part 1 of this series, scientists have created a model known as the kinetic particle model of matter to describe how solids, liquids, and gases behave. The kinetic particle model of matter says that matter is made up of tiny particles that are always moving. The way the particles that make up a substance are arranged, how they move, and how they interact with each other, determine the properties of matter in each of its three states. In fact, the kinetic particle model of matter is based on the following key hypotheses. First, all matter is made up of tiny particles.
Please keep in mind that the tiny particles that make matter might be atoms, molecules, ions, or electrons. It makes no difference whether these particles are atoms or molecules. We always represent them as a little ball. Even though it is common knowledge that atoms and molecules of matter do not at all look like an identical small ball, that assumption enables us to visualize what is happening inside materials on a very small scale.
Second, those particles are always moving around or vibrating.
Even the coldest object in the cosmos has particles that vibrate by a little amount. Particles just cannot stand motionless.
Third, adding heat to matter makes the particles move faster.
When the temperature of an object rises, the particles inside it simply move faster. When the temperature decreases, the particles slow down but never stop moving.
And finally, the particles attract each other strongly when they are close, but the attractions weaken if they move further apart. We now know how solids, liquids, and gases are different from each other in terms of their volume, shape, compressibility, and ability to flow, as shown on that table. In the next few minutes, we'll try to visualize the atoms and molecules that make up matter in each of the three states, using the kinetic particle model of matter. The relationships between matter particles will then be discussed in terms of the distance between the adjacent particles, their arrangement, the intermolecular force acting between them, their energy levels, and finally their movement. The physical characteristics of matter in its three states, as listed in this table, will then be explained using this knowledge as the foundation. But first, I'll expand this table to show a two-dimensional description of the particles in each state, along with their distances from one another, their arrangements, their intermolecular forces, their energies, and the types of movements they are capable of. As we now know from the kinetic particle model of matter, all matter is made up of incredibly small particles, which we now refer to as atoms and molecules, and in the case of solid matter, these tiny particles are arranged in a regular pattern, and packed closely together with very little space between them, as shown in this image. In fact, this image demonstrates how each particle is in close proximity to every one of its neighbors. Furthermore, due to the close proximity of the molecules, the intermolecular force will be much stronger than the particle's kinetic energy, and as a result of that, the particle won't be able to move around. However, they only vibrate while they are in their fixed position. If I want to draw a two-dimensional representation of solid matter based on the kinetic particle model of matter, I will start by sketching the wall of the container. Then I will start to draw the particles as small circles arranged in a regular pattern, as I am doing right now. Finally, you must make sure that the form of the solid matter will not take the shape of the container, because solid matter cannot flow. Additionally, to represent the particle vibration on solid matter, you can add two tip arrows to the particles. Okay, let us fill the table with the particles of the solid matter information. According to the sketch of solid matter we created using the kinetic particle model, the particles are tightly packed together, indicating that there is very little space between the matter's particles. Additionally, the particles are arranged in a regular pattern, creating a very strong force between them. That should explain why solid matter has a definite volume and shape, as well as why it is almost incompressible and cannot flow.
What about the energy and movement of the solid matter particles?
Okay. But first let me explain something about the particle's energy and the term thermal energy. Based on the kinetic particle model of matter, The atoms or molecules in a solid, liquid, or gas have kinetic energy because they are moving. They also have potential energy because their motion keeps them apart and fights the intermolecular force that is trying to pull them together. The total kinetic and potential energies of all the atoms or molecules in a material are called its internal energy. The hotter a material is, the faster its particles move, and the more internal energy it has. In fact, the term thermal energy is often used to mean both internal energy and heat energy. Solid matter has the least amount of potential energy because its particles are so close to each other. They also have the least amount of kinetic energy because they just vibrate around their fixed position. Because of this, we can say that the energy of solid matter particles is low, and that their movement is to vibrate. Again, based on the kinetic particle model of matter, these two sketches of liquid matter show that the particles are not as close together as they are in solid matter. Each particle is still in close contact with most of its neighbors, but there are fewer of them. The particles also vibrate so fast that the forces of attraction can't hold them in place, and they can move past each other. For a two-dimensional representation of liquid, based on the kinetic particle model of matter, I'll start by drawing a sketch of the container's wall. After that, I'll begin to draw the particles as small circles in a random pattern, but you must ensure that the shape of the liquid matches the bottom of the container, because liquids can flow. To represent the particles' motion, I'll draw several arrows in random directions to show the particles moving and passing each other. Alright, let's update the table with information about the particles that make up liquid matter. Our sketch of a kinetic particle model for liquid matter shows that the particles that make up liquid matter are more spread out than the particles that make up solid matter. So it makes sense to say that the particles that make up a liquid have some space between them. Since there is more space between the particles of liquid matter than between the particles of solid matter, we can say that the intermolecular force between the molecules of liquid matter is less strong than that of solid matter. This means that the particles of liquid matter can move and slide past each other. This makes them randomly arranged and gives them a medium amount of energy, compared to the low energy of solid matter. For gaseous matter, the particles are widely separated from one another. They are no longer in contact unless they collide with each other. For example, in air, the average separation between the particles is about 10 times their diameter. So, to make a two-dimensional picture of gaseous matter, first, I'll draw a picture of the wall of the container. But as I'm drawing a sketch for gaseous matter, I'll draw a closed container, since gas is easy to get out of its container. Then, like I'm doing here, I'll draw the gaseous particles as small circles that are randomly arranged and farther apart from each other. To show how the gaseous particles move, I will draw arrows pointing in all directions to show how the particles move randomly, and can even hit the side of the container. Now let us continue filling our table. Particles of gaseous matter have large spaces between them, are randomly arranged and held together by very weak intermolecular forces, have the highest energy level, compared to solid and liquid matter, and their particles move quickly in all directions.
The information in that table covers the displayed subject content topics for thermal physics in the Cambridge IGCSE Physics 0625 curriculum. I would ask that you pause the video so that you may take some time to comprehend the information.
Now that we know the kinetic particle model of matter, let us return to the temperature time graph and try to explain why matter changes states as the temperature changes. In fact, we need to answer two questions. The first question is why it takes time for matter to change from solid to liquid after it reaches the melting temperature, and why it similarly takes time for matter to change from liquid to gas after it reaches the boiling temperature. The second question is why matter needs more heat energy to change from liquid to gas than from solid to liquid. Before using the kinetic particle model of matter to answer those questions and explain why each state of matter has its own distinct properties, let us first understand this graph. On this graph, the time is shown along the horizontal axis, while the temperature is represented along the vertical axis. And as we mentioned in part 1 of this unit, we maintained the heat energy transfer to the matter on that experiment at a constant rate. For example, if the heat energy is 10 joules per second, after 2 seconds there are 20 joules of heat energy added to the matter, after 3 seconds there are 30 joules, and so on, meaning that as time passes, more and more heat is added. Also, the graph shows that the temperature of the matter changes as more heat energy transfers to it, while we observe a change in the state of matter from solid to liquid to gas. Now, on that graph, there is something that has to be explained. Despite the added heat energy, the temperature remains constant during both of those time periods, which is the first question we need to answer. Why does it take time for matter to change from solid to liquid after it reaches the melting temperature? And why does it similarly take time for matter to change from liquid to gas after it reaches the boiling temperature? Also, the boiling time is longer than the melting time, which means that more energy is needed to change the state of matter from liquid to gas than to change the state of matter from solid to liquid, which is the second question we need to answer. Why does matter need more heat energy to change from a liquid to a gas than from a solid to a liquid? Let's first divide the graph vertically into the various states of matter. Solid matter turns into liquid. Liquid turns into gas. Also, we can divide the graph horizontally based on the state changing point. Here we have the melting point, and here we have the boiling point. Because we will be trying to understand a temperature graph, let us review the temperature definition based on the kinetic particle model of matter. Temperature is defined as the average kinetic energy of particles in an object.
To put it another way, the particles of a substance move faster on average as the temperature rises.
Okay, let's begin at the point of origin, when matter was in its solid form at a temperature lower than its melting point. When heat energy is applied to the solid matter, the heat energy is then transferred to the kinetic energy stores of the particle's internal energy, which causes the particles to vibrate more and more strongly. As a result, the average kinetic energy of the particles increases, raising the temperature and increasing the spacing between the particles. When the temperature reaches the melting point, some of the particles acquire sufficient kinetic energy to break some of the bonds. However, the average kinetic energy per particle does not change, because any heat energy transferred into the internal energy of the substance is going to be used to break the bonds, not increase the temperature. So the temperature remains at the melting point until all of the solids turn into liquid. When all solids turn into liquid and heat energy keeps being added to the system, the temperature starts to rise again, as the particles in the liquid gain more kinetic energy. At the boiling point, adding more thermal energy doesn't make the liquid any hotter. This is because the extra thermal energy is used to overcome the forces between the molecules, instead of making the liquid hotter. When all of the liquid has turned into gas and more heat energy is added to the system, the temperature begins to increase again, as the particles in the gas gather more kinetic energy.
In fact, we will cover the temperature's effect on gas state in more depth later in our curriculum, as well as how temperature affects gas volume and pressure. The concepts represented during the explanation of this graph are an important part of your curriculum. Therefore, we will go over various past paper test questions regarding those concepts at the end of this unit, to make sure you have a firm grasp on them. You may always go back and revisit any of the topics addressed in that video by clicking on the link in the video description below.
Goodbye.